Hello, this video is covering the content in Unit 2, Module 3b, which is centered on once you build a molecule, what is the electronic domain, molecular domain, what is the shape of the molecule, what are the angles involved. Right, so we have N2H4, so to be able to determine the electronic domains, we need to build the molecule. Now initially it looks fairly, might look very challenging. 2 nitrogens, 2 hydrogens, how are they bonded? Well, if we look at nitrogen has to be the central atom, or at least both of them. And there's 2 ways nitrogen can bond. It can bond this way with 3 single bonds, or it can form a double bond and 1 single bond. Now in this case, it's going to be the second structure. We can build the molecule this way. And now we have a double bond. Each nitrogen has 8 electrons. Each hydrogen has 2. Right, so we start looking at the domains involved in the electronic domains around each nitrogen. Well, we count them up. So a double bond counts as a domain, a lone pair counts as an electronic domain, and a single bond counts as one domain. So a total of 3 electronic domains, which is trigonal planar. And now if we want to determine the molecular domain, see that there's only 2 molecular domains leading to the bent or angular molecular geometry. If we wanted to report the angle, this would be the angle here. Then we would, since it's trigonal planar, we think of it as 120 degrees. But because of the lone pair that's involved, it's less than 120. And that is due to the additional electron-electron repulsions that force the angle down, so it makes the angle smaller. Okay, so this is a very unusual bonding pattern for oxygen, so I thought I'd cover it. So when we look at oxygen, these are the common bonding patterns. So we started off with oxygens making 2 bonds, and this is all neutral oxygens. 2 bonds, you either do 2 single bonds or 1 double bond. Now we saw when we were building molecules like SO3 and CO3 that we can also have a 1 bonded oxygen, and that's with 3 lone pairs. But with 3 bonds, what does it look like? So we build oxygens, we start with this dot diagram. Then when we count the electrons, what we're going to do is we're only going to put 5. And you say, well, why 5? It's supposed to have 6. The reason we're going to put 5 is because there's a plus sign in this molecule, right? So there's a plus 5 electrons in the outer shell due to the plus sign. And now we see where these 3 hydrogens are going to bond, because we could put a hydrogen at each one of these sites. So that would give oxygen 1 lone pair here, and forming 3 single bonds. This is only possible for oxygen because it has a positive charge. Right, and just keep in mind, oxygen with the positive charge is very similar to nitrogen. It has the same number of electrons as nitrogen. And, okay, so what does this tell us about its molecular geometry? Well, if we count up the domains, there are 4 domains, 3 single bonds, and 1 lone pair. So that gives us a tetrahedron, electronic tetrahedron. But because there's 1 lone pair or only 3 molecular domains, we're in trigonal pyramid. So if we look at the angle here, the angle, because it's tetrahedral, would be 109. But because of the lone pair, the extra electron-electron repulsion, we put a less than sign. And that would give us trigonal pyramid. Okay, so here, instead of having a small molecule where you have to build it, we give you the molecule and we just ask you about all the different domains. So let's number them. Okay, first, let's number them here. So we'll go through all 8. All right, let's take a look. So 1 is N8, so a nitrogen with only single bonds. Right, so that's going to have an electronic domain of 4 because we include the lone pair, so 3 bonds plus molecular domains 3. So that means we have a tetrahedron electronically, but the molecular the domain is trigonal pyramid. Let's look at 2. 2 is we have a carbon atom with 3 domains. So 3 domains electronically, 3 domains with, so this is trigonal planar. That gives us 120 degrees. All right, so we go through 3. 3 is also a 3 domains. Remember, we keep the double bond is just 1 domain. Lone pair is 1 domain. So this is also an electronic domain of 3, but a molecular domain of 2. So this would be an electronic domain trigonal planar, molecular domain bent or angular. If we look at 4, 4 is a terminating carbon with only single bonds. The 3 hydrogens are not shown, only the bond from nitrogen. That's a tetrahedron. And we would get 4 electronic domains, 4 molecular domains. So it's tetrahedral electronically, tetrahedral molecular domain, molecular geometry. 5 is nitrogen with 3 bonds, which makes it the same as 1. 6 is a carbon atom, and we're showing 2 bonds, 1 to nitrogen, 1 to another carbon atom, items 5 and 7. And we have to provide the 2 hydrogens. So this is the same as for tetrahedral. If we go into 7, here we have a double bond, 2 single bonds. So this is an electronic domain of 3, molecular domain of 3. So this is trigonal planar. Let's see, did I change that? Yeah, trigonal planar. And then for 8, which is the one we get the most questions with office hours. So 8, it's an oxygen showing the 2 bonds. Lone pairs aren't there. So this is 4 domains, tetrahedral, molecular domain 2. So this is electronically a tetrahedral, but molecular domain of 2 gives it bent, molecular geometry of bent. So analyzing big molecules goes this way. I really encourage you to take the atom, take it out of its part of the molecule, count up the domains, and then it's fairly straightforward. Right, this question in the homework is asking about which of these 2 regions, 1 or 2, or possibly both, or neither, is generally planar. Okay, so what does planar mean? So planar means trigonal planar, and the only way we see trigonal planar is with molecules that have single bond, double bond combinations. So we start looking at the molecule, we immediately identify region 1 as a place where there are alternating single bond, double bonds present. This most likely is a trigonal planar portion of the molecule. While 2, yeah, there's 1 double bond present, but the rest are tetrahedrons. They're certainly not planar. And so for that case, we would consider 1 to be planar. Now, another aspect of the single bond, double bond combination results in resonance. So there's a delocalization of electrons throughout this portion of the molecule, in region 1. And what does that do? That lowers the kinetic energy of the system due to bigger molecular orbits. So this delocalization, resonance causes increased delocalization through bigger orbits. These bigger orbits now lead the remaining electrons. There's less electron-electron repulsions at each atom because of these electrons are now farther away, and because of that, potential energy goes down. And the total energy goes down because both kinetic and potential have decreased. Right, so which of the functional groups are present in this molecule? Right, so most students kind of come into the test with a page with some of these already listed, or you can memorize them. After you use them for a while, they're pretty easy to remember. So let's take a look at what each group represents here. So a phenyl is a carbon ring with alternating single and double bonds, which we talked about as resonant, and then we draw just a circle in the middle to represent it. Hydroxyl is a carbon attached to an OH, or an OH group attached to a carbon. That's the hydroxyl group. A carboxyl group is one in which you have what looks like a hydroxyl group, but it has a carbon double bond O, which affects its chemistry, and so we give it its own name, carboxyl. And then amine is a nitrogen group with 3 bonds and a lone pair. Okay, so we look at the molecule and say, yep, we have a phenyl, we have a hydroxyl, and we have an amine. Oops. So those would be the 3 functional groups that are present in this molecule. All right, so let's take a look at a summary here. So for geometries, so carbon has these 3 aspects. They show all aspects: tetrahedral, trigonal planar, and they show linear behavior. Nitrogens pretty much have 2 different ways of bonding. Could have a double bond, single bond, or 3 single bonds. They always have a lone pair. And so these molecules with nitrogen are fairly straightforward. Where you say, can I build it with, does it require a double bond? Does not require a double bond. Oxygen, a little different, right? It can form 2 bonds, right? 2 single bonds and a double bond, but we saw a couple other possibilities, the most common being the one in which oxygen is forming a single bond and you just have a lone pair, an additional lone pair on oxygen. So instead of having 2 lone pairs, it has 3. Right, this leads to different domains. So there's only 3 electronic domains. There's the linear domain with 2 domains. There's the trigonal planar domain with 3. And then there's the tetrahedral domain with 4. Those are the only 3 electronic domains. So electronic domain must be linear, trigonal planar, or tetrahedral. And the bond angles are 180, 120, and 109. But the molecular domains is more diverse. We see that in the electronic domain of 3, we can have a lone pair. This often is present in nitrogen compounds. So nitrogen compounds can have a double bond, single bond, but it still has a lone pair. So this is a trigonal planar, but because it has a lone pair, it has those additional repulsions, making it bent or angular. Another molecular domain is there's 2 tetrahedral molecular domains that we have to consider if there are lone pairs present. Again, involving nitrogen. One is the all 3 bonds on nitrogen and 1 lone pair, giving us the trigonal pyramid. Or we could have the very common bent water, like the structure of water, but there's also other aspects of this in other molecules in which you have 2 single bonds to oxygen, and this is a bent structure less than 109 because of the additional, but it's still tetrahedral electronically. So there's still 4 domains in both of these with oxygen and with nitrogen. There's still 4 electronic domains, but because of the lone pairs, they are not molecularly tetrahedrons. They have these other designations. So that's the summary of how we assign structures and how we sort of hone in on the chemistry and structure of carbon, nitrogen, and oxygen.